So yeah, again, yeah, we are starting with the concept of equivalent circuit of three-phase induction motor today. And before that, as I said, we will be looking at some key points, the concept of slip and also the concept of speed, which we discussed yesterday. I won't be writing the all the speed related key points I have discussed in the last week, but I hope you remember all those points. But I will just write some key points related to slip. So yeah, coming to slip, we know the slip comes into picture whenever our rotor is rotating with some speed which is different from synchronous speed. If both rotor and stator are rotating the same speed, there is no concept of slip. Slip won't be there, and that's why it's called an induction motor, but not a synchronous motor. So S is equals to ns minus nr by ns, where ns is the synchronous speed and nr is the rotor mechanical speed, where we already discussed the units of all these ns and nr in the last class. I hope everyone remembers the discussion. If not, you can verify our last week's video lecture where I have mentioned all the formulas for ns and nr in terms of mechanical degrees and also radians per second, radians per minute, everything. Yeah. Now here ns is equals to 2f by p. The unit will be mechanical rotations per second. So this is fixed here. In slip formula we can see ns is always fixed, that is constant. Why it is constant? Because from this formula you can see it's 2f by p. Once the machine is fixed, number of poles is fixed, and once the supply is fixed, f is something but supply frequency. So ns is a fixed value, but nr changes with respect to your rotor speed. Now the range between the slip will be lying between will be 0 to 1. 0 is the least value of the slip and 1 will be the maximum value. So can anyone tell when will the slip be 0? The slip will be 0 when there is, whenever rotor is rotating and also stator is rotating, the rotor has some kind of opposing forces while it is rotating on the shaft. So at the shaft end, when you mount the rotor on the shaft, there will be some opposing forces, what we call friction forces, or if there is some load that our motor should drive, that the torque required to rotate that particular load. So these are the opposing forces that the rotor will experience. Based on that, because of that only, you will get some slip. So if there is no load and there is no friction, there won't be any slip. That is that's the condition where we call S is equals to 0. I'm just writing the condition here. There is no opposing forces. No opposing forces means there is no opposing torque for the motor to rotate, and not even friction. Not even friction is present. So that's why we call it, this case is not an ideal case. Ideally, there exists no case where the slip is 0 in case of an induction motor. So slip will always be there. And yeah, slip is equals to 1. Slip is equals to 1 means you can say from the formula, like mathematical, if you want to see S is equals to ns minus nr by ns, and S is equals to 1 when nr is equals to 0. That means nr is 0 means your rotor is not rotating, and it's we have blocked the rotor, we have locked the rotor. So that's why we call S is equals to 1 as a locked rotor condition. So you are not allowing the rotor to move. That's why the speed of nr is 0. So when you keep nr is equals to 0 in the formula, you will get S is equals to 1. That's the maximum condition where you can get the slip value to be 1. Now I'm just rewriting this formula, slip formula. S is equals to ns minus nr by ns. Now it's very famous formula which you also remember. Nr is equals to ns into 1 minus s, where nr is the rotor speed, ns is the synchronous speed. Both of them are in mechanical rps units, and 1 minus s, where s is the slip of the machine. Now yeah, this is one point I want you all to remember. And the second point is or I can say induced EMF. Yeah, so there will be a stator induced EMF as well as a rotor induced EMF whenever we give a supply from this three-phase supply V1. So excluding the resistances and reactance in the stator side, E1 will be induced in the primary winding. So that's what induced EMF we are talking about. And you all remember the formula for this induced EMF, that is E1 is equals to root 2 pi f phi kW1 N1, where F is supply frequency, phi is flux per pole, and kW1 is the winding factor, which we discussed in detail in the 2 weeks before class, where kW1 is a multiplication factor of Kp Kd, that is pitch factor and also distribution factor, and that is multiplied with the N1, that is the turns in that particular primary winding. When you multiply kW with the N1, you call it as a effective turns. So that's what the actual turns which will be useful. So that that discussion we already did. That's why I'm writing it again just as a points to remember. And yeah, this is the induced EMF which we see here. Now at any value of slip S, there will be rotor EMF. Let's say this is the stator induced EMF. So I'm writing it here. This is the stator induced EMF. Now because of this EMF and because of some slip present in the rotor, some EMF, some quantity of EMF will be induced in the rotor at any value of slip. So that induced EMF in the rotor at value of slip E2S, we call it as that one. So root 2 pi, and we discussed in the last week itself only the frequency with which the rotor will rotate. I mean all the electrical quantities within the rotor. If our supply frequency is F, the electrical quantities in the rotor, that is voltage and current that is across the secondary and also current through the secondary winding, will be with the frequency of SF, that is we called as slip frequency. So that's what we call it as a slip frequency or rotor frequency. Now the same formula we can write as root 2 pi SF, and flux will be there and winding factor kW2 N2. Now what is this SF? This is the frequency of all the electrical quantities in the secondary, or you can call it as rotor circuit. Here primary and secondary we are using the terms, but ideally we should talk in terms of stator and rotor. So quantities in the rotor quantity. So what are the electrical quantities, voltage and current, whatever that are in the rotor circuit, they will have a frequency of slip frequency, that is SF. Now yeah, if I separate S term and write it like this, root 2 pi f k W2 N2. Now if you see this condition where S is not there, so there is no condition of slip here. So what I can replace this value by S into, I will term it as a E2, where where I call this E2 as induced voltage in rotor. That is, of course, it's per phase. We are talking in terms of per phase induced voltage in rotor at S is equals to 1. So S is equals to 1 is nothing but what we call lock rotor condition, or you can also call it as a standstill condition. Standstill means there is no movement in rotor. So at that condition you can get NR is equals to 0 and NS minus NR is equals to NS. So there you get slip is equals to 1. So now if you see this formula, induced EMF formula, E2 is the rotor induced EMF, E2S means rotor induced EMF at any value of slip S. I have wrote the formula and take S outside, and the rest, the formula that is left will be the rotor induced per phase voltage in rotor at S equals to 1, which is nothing but the standstill condition. Yeah. And also if you take that E2 and E1 by E2, if you do, it is nothing but kW1 by N1, it is kW2 by N2. Rest all factors are same. Now you call this as what? You call this as a turns ratio, or you can call it as effective turns ratio. So yeah, simply because all the other factors except for KW2 and N2 N1 and KW1 N1 are same, so they cancel out, and we will get this kind of relation. So now let's draw the equivalent circuit of the induction motor per phase. Let's say our rotor is stationary, and we have applied the voltage in the stator, that is from the supplies we applied the voltage per phase. We have given some, say, V1 per phase voltage we have applied. So I'm just drawing it here. Let's take a star connected stator, and I'm saying at S is equals to 1 means standstill condition. So what I want to discuss here is, so E1 by E2 we are having an effective turns ratio, and also the frequency at S equals to 1, we discussed that rotor frequency and stator frequency will be what? It's same, because whenever there is slip there exists a slip, my rotor frequency becomes SF, but when S is equals to 1, your rotor frequency will also equal to F. So because FR is equals to SF, I'm just writing it here. At S is equals to 1, FR is equals to SF is equals to F. So what I'm trying to say, at S is equals to 1, the circuit is just like a transformer, because we have energized a primary winding with a 50 Hz source, let's say, and our secondary is short circuited, because in an induction motor we short circuit the rotor, so secondary is short circuited, and the frequency at both primary and secondary side are same, that is F frequency, that is supply frequency only, and also the voltage induced in both rotor and stator here, that is primary and secondary, E1 and E2, if you take the ratio, we are getting a turns ratio. So we are getting a turns ratio by dividing the voltages, and also we have a frequency in both stator and winding, rotor winding as a same. So with this kind of behavior, we will get only in a transformer, right? So that's why we say whenever slip is equals to 1, the circuit is just like a transformer. So what happens is, in a transformer, what exactly transformer does? So transformer principle is nothing but it changes the given voltage, whatever we give it the primary, it changes the voltage into another level of voltage without changing the frequency. So that's what transformer do. It's a static device, and whatever voltage you have given in primary, based on the turns ratio, it will shift that voltage to another level, keeping the frequency constant. So at this S equals to 1, equivalent circuit of an induction motor will just be like a transformer circuit. So we are approaching the equivalent circuit of induction motor through transformer principle, because we already discussed the equivalent circuit of transformer in last electrical machines 1 course. So you all remember what happens in a transformer and what exactly the equivalent circuit of a transformer looks like. So at S equals to 1, the equivalent circuit of an induction motor is nothing but the equivalent circuit of a transformer. So yeah, there will be a stationary resistance, stator resistance in a equivalent circuit of transformer, and there will be a leakage reactance. So those two will be R1 and X1, and there will be a magnetizing branch, if you remember, that is in parallel, XM we call, that is much higher than the magnitudes of R1 and X1, because XM is a magnetizing branch, and the current flowing through the magnetizing branch will be magnetizing current. So you know the current required to magnetize the core will be much more than the primary and secondary currents. So that's why XM value is much higher, and based on this leakage reactances and resistances R1 and X1, there will be induced voltage even across the winding. So if we neglect the values of R1 and X1, total input supply voltage will appear across the winding, that is E1. So okay, 1 second, someone has joined. Yeah. So I'm trying to draw the equivalent circuit of transformer first, assuming that S is equals to 1, because we just checked that at S equals to 1, my induction motor just behaves just like a transformer. So yeah, let me draw the equivalent circuit of a transformer now. So this is the primary and V1, this is the per phase supply voltage V1. Let's say I have been given this voltage to a single phase now. And yeah, as we just mentioned, this is R1 and X1. These are the stator resistance and leakage reactance R1 and X1. And then we will have the magnetizing branch. So this is XM. So we are using the capital letter for XM just to represent that it is having a much higher value than the leakage reactance and also the resistance. So the voltage induced here, that's what we call will be the induced voltage E1 here. Now let's say this is stator. We already have a stator circuit here. Now V1 I am giving a supply here. So this will be the E1. This will be the E1, and yeah, this connection will have a R1 comma X1 on the primary side. That's what stator side we are calling it. Now yeah, this is the primary side circuit. Now if we see the secondary side equivalent circuit of a transformer at S is equals to 1, again that's what we are assuming. So induced voltage will be E2. Just now we saw this particular E2 is what the standstill condition induced voltage. Then only the slip won't come. Now induced voltage is E2, and there will be secondary voltage. So we just talked E2 is induced in the secondary side, and again secondary side will also have its own resistance and leakage reactance. Now yeah, this is R2 and this is X2, and yeah, the all quantities in the secondary side will have a frequency of F. It's not SF because S is equals to 1 here. So let me draw again star connected rotor, and yeah, I have short circuited the rotor circuit, and there will be E2 here, and F is the frequency of the electrical quantities in the rotor. Yeah, secondary sorted. So we want to make it like a induction motor. Induction motor, if you take, we have shorted the rotor circuit. You can, if you want to draw some current here, you can remove the short circuit and you can connect some load. That's how you will draw some current in the secondary. No, in transformer we don't short. We are trying to approach the equivalent circuit of an induction motor when stationary condition, the condition stands still. So at standstill condition, the characteristics of induction motor are nothing but a transformer. That's why we are replicating the equivalent circuit of a transformer using replicating the equivalent circuit of an induction motor using the transformer side. The secondary is not short circuited in the transformer, but in induction motor rotor circuit terminals are short circuited. So that's what we mentioned here. So if you want to yeah, it's stationary here. It's stationary at S equals to 1 I mentioned here. So it's in a standstill condition. So yeah, this is how a equivalent circuit for a induction motor will look like when S is equals to 1. Now I will just quickly write the parameters here, whatever you are seeing on the screen, R1, X1, XM, and here it is R2 and X2. And yeah, R1 is stator resistance per phase. So X1 is stator, exactly, total stator leakage reactance per phase. So all quantities are per phase. Even if I forget writing per phase, it is per phase only. So you have to make sure. XM is magnetizing reactance. Now R2 is rotor resistance per phase, and X2 is rotor leakage reactance per phase. So now looking at all these parameters, you can say R1, all the R2, these resistances are not dependent on the frequency term, so they don't change with respect to frequency. But if you look at the reactances, so X1 and X2, they are dependent on the frequency. Why it is dependent on frequency? Because you have a reactance, and if you want to calculate the impedance of that, the formula is omega L. So that's inductance, and also omega is equal to 2 pi f. Within the 2 pi f you have the frequency term there. Now whenever you are calculating the reactance of a specific equivalent circuit, you have to take into condition of the frequency at which the circuit is operating as well. So then only you can get the actual impedance that particular reactance is offering, because that the values keep on changing with respect to the frequency. Now, so yeah, I just want to say that, but when motor runs, let's say our motor is rotating, and your rotor frequency will change because there comes a condition of slip into picture. Now the rotor frequency will change, FR will comes into, FR will keep on changing when your slip keeps changing. So the reactance value must be modified every time. Now let's say we connect the primary and secondary circuit using now we have two circuits, right? Primary side equivalent circuit and secondary side equivalent circuit. Now let's say we want to combine these two equivalent circuits. Using some circuit analysis, we can just do it simply, and we can get the entire equivalent circuit refer to one side. Now I have the rotor side, I have the stator side. I can refer all the parameters from the stator to the rotor and combine it, or I can refer all my rotor quantities to the stator side and then also combine it. So anything I can do, but I can combine these two, primary side and secondary side, using such circuit analysis, and we can just get a combined equivalent circuit. So I'm again writing it at S is equals to 1, FR is equals to Fs is equals to F, that we already got because S equals to 1. So it's just like a transformer, and also E1 by E2 is equals to turns ratio, and yeah. Now let's draw equivalent circuit referred to stator at S equals to 1. So this is important because we are indirectly eliminating the concept of slip here. Later we will see what happens when slip comes into picture, but right now S equals to 1, that is standstill condition we are writing. And yeah, this is V1, and yeah, this is R1, this is X1 leakage reactance, and yeah, this is what, this is the magnetizing reactance XM, and yeah, there will be the rotor side leakage reactance referred to stator, and this rotor resistance referred to stator. Now the value of this will be multiplied by the square of the turns ratio that you already know. So I'm just writing it here, a square x2 and a square r2. So there is no slip, slip is not present in the entire equivalent circuit. At slip is equals to 1, we got the equivalent circuit referred to the stator. Now the question is, what will be the equivalent circuit of my three-phase induction motor when my slip is not equals to 1? I mean, my rotor is actually rotating, but it's not in the standstill condition anymore. Now what we'll have to do, so let's get, that's the question here. Equivalent circuit when S not is equals to 1. Again, let's get back to our original discussion where we have two different equivalent circuits, primary circuit and also secondary circuit. Now within the secondary circuit, now we have the concept of slip. Now the terms which are affected by the slip, we have to take care of the slip in the secondary side. I will just write it here. The stator will remain same. The stator circuit is not modified because there is no slip in the stator. I'm just writing it R1 and X1, and I've given a supply V1 here, and we have XM. So yeah, this is the E1 that is generated here, and this is R1 and this is X1. So this is primary side, so that is clear. Now coming to the secondary side, we already discussed the rotor induced EMF when the slip in comes is S into E2, that we already just saw in the first slide. Now there is a reactance in the secondary side that changes with respect to the frequency, right? So then also our parameters in the secondary side will change. So I am writing here E2. It's not E2 anymore. It's S into E2, and R2 is there, and one reactance is there. Okay, and this is R2, and this is SX2. It depends on slip. When it comes into frequency, comes into picture. So that's why it depends on slip. Now, yeah, there flows some circuit in the rotor, that is rotor current, and the quantities, electrical quantities in the secondary will have a frequency SF. So yeah, so this is what we are seeing here. This is FR is equals to SF, and now frequency in primary and secondary is different. In primary we have a supply frequency F, in secondary rotor circuit we have a SF, slip frequency. Now my X2 will become SX2 and E2 will become SE2 because my frequency became SF. Sorry, excuse me. So this E2 we at is equals to 1, that is at standstill condition. Now it's not a standstill anymore. Now my rotor is rotating with some speed, that's why slip came into picture. And one more thing you have to notice is, if you take the turns ratio now, this is E1 and this is SE2. If you do SE1 by SE2, it's not anymore the turns ratio. It's not equals to A now. So yeah, with all these coming into picture because of slip, it's getting bit different, and now we can't even combine these two circuits because the turns ratio is not A, and we can't just multiply with the term A square and get a stator referred equivalent circuit altogether. Sorry. So yeah, how to overcome this problem? So this particular problem you need to keep in mind, because we will discuss some transformer concept now, and we will arrive at this problem again, and then we will see how we have overcome this problem. So this is the question. So I'm writing the question here. So how to find equivalent circuit of induction motor when S naught is equals to 1. How to combine primary and secondary side equivalent circuits when S not equals to 1. So this is the question. Now let's try to understand. So let's say our motor is operating with some kind of slip S, and also our rotor current is some I2 value we have. We can get the value of I2 current at operating at the slip frequency, and at any instant we can or you can just write it here only. So if you are seeing this rotor circuit here, right? So to calculate the I2 here, what is the formula using KVL? Can anyone say what is the value of I2 here? You have the voltage and you have the impedance. What's the value of I2, RMS value of rotor current? Yeah, under root of, exactly. So exactly correct. That's what if you want to calculate the RMS value of rotor current under this frequency SF, it's nothing but my voltage in the secondary rotor circuit is SE2 divided by the equivalent impedance in secondary, that is nothing but the under root R square plus SX2 whole square. Now this is what my current. So this is very important point. Rotor RMS current, it is I2 is equals to SE2 divided by R2 square plus SX2 square. Now if you want to rewrite this, I'm doing nothing. I'm just taking the slip from the numerator into denominator, and I am doing some kind of change in the circuit. I'm just writing another expression, and I will ask you all some question. one question and you tell me whether it is right or not. So are these two same or not? E2 divided by R2 by S whole square plus X2, is it same or not? Yeah, they both they both are exactly same. Here the both the magnitude of I2 in the top and the magnitude of I2 in the below are same. So let's say the equivalent circuit for the top one is just we discussed. It's SE2, it is R2 and it is SX2, and the equivalent circuit of this one will be it is E2, there is no more S in the voltage induced here, and it is R2 by S, my resistance value, and here it is X2, it is S equals to what, like now my X2 is standstill reactance because S is not there. But in both these circuits, the current flowing in this circuit I2, and here it is also I2, my both currents will be same. That is very important. Even if we rearrange the circuit, if we have changed the value of resistance and some rearrangement we did and we got the circuit, in both these circuits, the top one A and B, if we consider, the magnitude of rotor circuit I2 is same. So yeah, now a small transformer concept we will talk, that is very important transformer topic. Let's say we have a transformer, and let's say in a transformer, as someone pointed out, secondary is open circuited. Yeah, let's take a transformer and let's say my secondary is open circuited, and in this condition my primary current will only draw a magnetizing current because there is no load connected to my transformer, and to set up the flux in my core, the amount of current needed is only needed to magnetize the core. So that's a concept of the transformer. So I have open circuited the secondary, and just so yeah, this is my transformer primary and this is my transformer secondary, and I have given some supply here and I open circuited the secondary, and this current drawn by the primary winding is only utilized to magnetize the core. That's why we call the circuit as the current as a magnetizing current. Now the moment we try to draw some current from the secondary, let's say okay, my core has magnetized, that's done, but now I want to utilize my transformer to some load, I want to drive some load. So what I do, I want to draw some current from the secondary. So now what I do, I will just try to connect my secondary with some load. So whenever I close the switch, definitely current will pass through the load, that let's say that is I2. Now what I'm trying to do here, we are trying to draw some current from secondary by connecting some load via a switch. Let's say I have closed the switch now. Now no matter what we do in the secondary side, open circuited or closed circuited, we know that the flux setup in the core is always constant. So see, there is no load connected before, my core is magnetized, the flux has been set up. Now the flux is being maintained constant. Now I have connected a load here. Now my secondary has drawn extra current. Now from where the extra current is coming, because my flux in the core will always have to remain constant. So when my flux in the core is always fixed, and I am asking the secondary to draw extra current I2, from where that current should come? Because primary side I am not changing anything, the supply is fixed, and whatever current will flow I have no control over it because that is already fixed. For this kind of voltage, it will draw that current, and my secondary was open circuited then. Now I have tried to draw some current in the secondary, and that made I2 current flow in the load. So from where the current is coming, my secondary gave that current. But you have to understand this important concept here. There always exists MMF balance in a transformer. So N1 I1 is always equals to N2 I2. So that what keeps this MMF balance. So see here, in open circuit condition, when there is no current flowing in the secondary, the current required I in that condition is only magnetizing current. So the supply, the current drawn from the supply is I only. Now what I said, in this condition, in the second condition, I have tried to connect some load across my secondary, and the current drawn by the secondary is I2 now. Now whenever I am doing these changes, my stator will not sit quietly. What my stator will do, so okay, stator means the primary side here, sorry. So my primary side circuit will not sit silently. So what it will do, because secondary whatever current it needs, it has to come from primary only. So in this condition where there is open circuited condition, and now this is primary current in loaded condition, my primary side is forced to draw some additional current, let's say I2 dash. That additional current I2 dash, it balances out the I2 in the secondary side, because the concept is, once my flux is set up in the core, that flux should remain constant. So because of this additional current drawn by the secondary, there is additional MMF is coming into the secondary. That is, MMF is something that Ni, turns multiplied by current. So there exists some N2 I2 is coming into the picture. So now I have to recounter it, because my flux should always remain same. So because of this additional inclusion of this MMF, my stator circuit is forced to draw additional current from the supply, that is analogous, that is I2 dash, so that N1 I1 dash and N2 I2 dash are exactly equal but opposite in polarity. Because into the dot convention, if you see here, the dot, the current is entering, and here the dot, the current is leaving. So that's how the MMF balance will come. So let's say the MMF N2 I2 is by the rotor, and by primary N1 I1 dash, it will I2 dash, sorry, N1 I2 dash, it will produce, so that these two are exactly equal and opposite, and they will cancel upon each other, so that again my flux balance is achieved. So this is what very important concept which you have to remember. In both cases, my stator side has no change. I have not connected any extra circuitry in primary, but my primary side senses that there comes a additional component of current in the secondary, due to which my primary should draw some more current, which is not just a magnetizing current, but also some additional component of current to counterbalance the MMF produced in the secondary. So that's the principle we have to keep in mind here. So from how it is managed to do that, so how my primary managed to do that. So if you want to see it again, so under no load condition, my primary is drawing only magnetizing current, so that is needed to establish the flux. So in the second condition, so the moment we close the switch here, my secondary current will my secondary winding will experience some current, my secondary will draw some current. So this extra MMF which we are seeing here, which is, we have brought this extra MMF into the system. So before there was no this, this extra MMF does not exist. Now we have brought some new MMF into the system. Now since my load is connected, this extra MMF came into picture. Now this must be balanced. So to balance this MMF, my primary must draw some additional current along with this magnetizing current. So this additional circuit, we call it as a reflected current, this additional current. So this is important. So this concept of drawing reflected current is very important to attain MMF balance in a transformer. Now if you see here, I have IM, that is magnetizing current I have wrote here, and I2 dash component is to be additionally drawn by my primary, which I am calling it as a reflected current. Now this, because of this I2 dash, my value of I2 dash is such that N1 I2 dash is exactly equal to my N2 I2 dash. Now these two MMF which we are seeing here, they cancel out, and therefore my flux in the core again remains same. That is nothing but due to the magnetizing the core. So whatever flux that is needed to magnetize your core, that shouldn't change, that must not change, because let's say you need some flux to magnetize your core. That's it. To magnetize your core, to establish that magnetizing flux, you need to pass certain amount of magnetizing current IM. That's it. You already provided the IM, and based on that IM, you have generated some magnetizing MMF, that is N1 IM. So now that amount of flux should only be present for magnetizing the core. There should not be any other extra component of current that needs to be drawn. But if it is drawing some additional component of current from the supply, it is only because to counteract the MMF present in the rotor circuit. So that's very important concept which you have to keep in mind here. Now, after this discussion, I want to summarize it in the 2 points. Now, what I'm saying here is, so if you have an unloaded secondary, that is my secondary of the transformer is open circuited here. So you see this, the current drawn by the transformer primary is only magnetizing current. That's the first point. So yeah, if you want to take a note, you can take a note, or you can just remember it. So if transformer secondary is open circuited, or you can say unloaded, my current drawn by the primary is only IM. It's only magnetizing current. Why I am writing these points here is very important concept in transformers. It's the base of transformer. Why it's drawing the current, why it is not drawing some current. That's why it's very important. So yeah. Now second point was what we have to write here. So if you closed your secondary with some load now, like let's say with this help of switch, you have connected some impedance across the secondary. You will secondary will draw some current, and your primary cannot just stay silent and look at this change, but it will also draw some additional current. It is IM plus I2 dash. That's what I'm trying. If transformer secondary is loaded, I mean you connected with the help of some switch, you have connected some. Now current drawn by the primary is IM plus I2 dash. Excuse me. If it's I2, then it's I2 dash. My setter will not sit silently, but it will immediately react by drawing some extra current I2 dash, such that MMF balance will occur. That is N1 I2 dash will always be equal to, I will also write that, N1 I2 dash is equals to N1 I2. So yeah, sorry, yeah, this is what my concept is. Now the total MMF existing in the circuit, if we calculate now again, that is N1 IM, that is my magnetizing flux, plus N1 I2 dash, that is my flux generated by my primary additional current, minus N1 I2. So if you take the notation as minus, and it will become plus, and it is minus, it is become plus. So finally they both are in negative direction, they will both cancel out. The total MMF in the core remains constant even now. So yeah, that's the concept. You have to make sure always my flux remains same. So you don't have to do anything. That is the internal property of transformer. So whenever you connect a secondary load, so based on the current drawn by the secondary, the same amount of current which is that has to be drawn by your transformer primary supply supply side, so that your MMF will be counterbalance. Now we will take this particular concept of transformer into our three-phase induction motor. So we have started with the problem. What's the problem? So how can we combine two circuits of primary and secondary where a concept of slip exists in the secondary? How can we combine it? So that's what brought up the question, and then we came to the discussion here where the concept of drawing some additional current and all. Now if you see, I will just take a new sheet, and I'm trying to write, say, for the same concept I am trying to bring it to the three-phase induction motor. Let's say I have energized my primary again with some three-phase voltage, and RMF will produce, and it will induce some voltage. Okay. Whenever EMF is induced, and also before, the reason for induced EMF will be there is a time varying flux, and there will be, for each pole there will be some flux that we call as flux per pole. And if we neglect the R1 and X1, the whatever supply we have given, that will appear across the windings, that is V1 is almost equal to E1. So I'm just writing E1 root 2 pi f phi. This phi is flux per pole, and again I'm writing, so this will be almost equal to V1 if R1 comma X1 are neglected. If not, V1 can never be equal to E1. So that's you have to keep in mind. From this formula which we wrote, what will be the value of flux? V1 divided by root 2 pi f k w1 n1. So this is the formula of flux we get here. Now whether my secondary is open circuited or connected some load or whatever it is, whether it is short circuited or I have connected some impedance or it is open circuited, I know the amount of flux it needs to set up to magnetize the core. Now just now we discussed the concept. I know what amount of flux per pole it is required to magnetize my core. Now I know the value here that you are seeing directly here. Whatever I do to my secondary, whatever I do to the rotor terminals of my induction motor, it should always give the same amount of flux what you are seeing here. That's the concept we just discussed. I hope you all agree for it, because this particular flux per pole, no, yeah, exactly. If your circuit is open or closed, your flux in core should remain same. So because that flux you are giving to magnetize the core is always there, and you need some flux. That's the value you are seeing here. So this flux per pole, the value you are seeing here, should remain constant. Now you also remember, like, flux formula we have seen we have solved the problem in 2 weeks before, and we have did some derivation also, from where we have saw B net divided by P into L into D. So this is already where D is equals to nothing but 2R. So we have seen this formula. Now let's say this is the flux we need to establish in the core so that it will be magnetized. Now this, what we are trying to say is, this strength of this magnetic field B net we are seeing here, that will remain same from no load to full load operation. No load to full load means open circuit condition to short circuit condition or full load operation. Now as this concept is clearly understood now, clearly established, now this flux should remain constant within the core that will help to magnetize my core. Now let's close the switch in secondary side of our machine, and let's see what MMF needs to be taken care of, because whenever we close our switch in the secondary side of our rotor circuit, we know it will definitely draw some current, that is I2 that will flow. So my primary side will be forced to draw I2 dash, just like we saw in the transformer now, such that my MMF is being taken care of. Now yeah, again I'm saying this magnitude of this B net, this is the strength of my magnetic field, must remain same, which is same as which because I'm saying that this flux per pole which I'm seeing should remain same. Now I'm just writing it here. Let's say I have my rotor circuit, star connected rotor circuit. You can also do it in delta, not a problem, but usually we don't do it in delta because it's a bit complicated. So yeah, let's say we have a short circuited rotor. This is the induction motor. I'm trying to take the concept of transformer into induction motor now. At this instant, so yeah, this is secondary again. At this instant, there flows some current in the secondary. I'm sure there will be some current will be flown, and in this phase there will be some I2 current flowing, because let's say this is my primary, And as I said, we are applying this concept to my induction motor. I have given a three-phase supply here, and there exists some RMF. RMF will be produced, and there will be some, let's say my stator field is having an NS, and then I have closed the secondary side with the help of a switch, and the secondary current will flow now. Now, what is the secondary circuit? So we already discussed that value here. That's where, so see this one. So this is the condition. This is the place where we stopped our discussion. This is the question it got erased. So how to find the equivalent circuit when s not equals to 1? And we know there exists some rotor RMS current in this condition, that is I2. So let's continue the discussion from here. Now the current will be I2 is equals to SE2 divided by R2 square plus SX2 square. I hope this point is clear. This we already established now. Now the question comes, how we are going to use that concept here. Now there exists a stationary observer who is sitting on the stator, because stator is always stationary, it won't move, but the field of the stator will move with the speed of synchronous speed, that is ns. Whether let's say one observer is there, he is sitting on the stator and he is observing the speeds of the fields of this stator and rotor and whatever he is observing. Now with respect to the stationary observer, the speed of the rotor field is, if anyone remember the speed of the rotor field and stator field? We discussed in last class in very detail. Yes. No, that is slip you are talking about. So no, in the last class we discussed that both stator field and rotor field, we are not talking about rotor mechanical speed, it's the field speed. The speed of rotor and stator field is always ns with respect to a stationary observer. So here a stationary observer observing the speed of stator field and also the rotor field, he will notice that both fields are rotating with the speed of ns, but this is not a mechanical speed of rotor. If we talk about the mechanical speed, it is nr, but the field produced by the rotor and stator is always rotates with the same speed, that is ns. Now this is an actual motor condition we have right now. The speed of rotation rotor field is ns, and the frequency of the electrical quantities in the rotor side is sf, and this is the magnitude of current of our actual motor condition. Now I want you all to imagine a induction motor. This is some fictitious motor we want to discuss now. So this is what our actual motor condition we have stuck at this point. Now we have come across a problem how to join these two circuits when slips comes into picture. So this is our actual motor. Now forget about this actual motor and imagine induction motor now, which is stationary. That's very easy to assume, because at stationary there is no concept of slip. Now my I'm just skipping imaginary induction motor. Standstill. I am just listing out the conditions and characteristics of my imaginary motor. Standstill condition. Now S of this imaginary motor is 1 now. So there is no concept of S. Let's not write and confuse it here. And standstill condition, and my stator is same as stator, winding and supply, everything is same as my old actual motor, and rotor connection, star connected, and the values, everything is same. The rotor is also same, having the same field and all, but I am changing a small value in this rotor circuit, that is, except my rotor resistance value R2, R2, rotor resistance, yeah, R2 by slip. You are exactly correct, but what is this value of the slip? Because I already told you the imaginary induction motor is having a standstill condition, but from where this slip is coming. You understood, right? I have changed the value of resistance to R2 by S, but I asked you to remember. I asked you to imagine that a new imaginary motor in a standstill condition. But again, I am saying now, I am changing the resistance value of R2 by S. But how? Why is this S coming to picture? No, no. Actually, the value of R2 by S is a fixed value. I am giving it to the rotor resistance. This S value here is nothing but this S value. I am taking the value of S from here, where S is the slip of actual motor. There is no slip in this imaginary, but I am just using the value of slip there, and I am calculating my own resistance R2 divided by S of the actual motor. This is very important because there is imaginary motor, this standstill condition. I'm imagining a motor of a standstill condition and changing the rotor resistance to a value of a physical fixed value of R2 by S, where I have taken the S from my actual motor. So now I have my actual motor. I know the value of the slip there. I have taken that value of the slip, and I have calculated my R2 by S new resistance value, and I'm just writing the conditions of here. Now in the secondary circuit, my rotor is standstill. I mean the rotor is locked, and my reactance, leakage reactance is X2, that is standstill reactance, and my value of resistance is R2 by S. So this is the conditions of my imaginary motor. There exists a resistance, there exists a standstill leakage reactance, my rotor is locked, and the value of my rotor resistance is exactly R2 by S. I have calculated the R2 by S value by taking the slip of my actual motor. Now, okay, it's I have to take more. Yeah, so yeah, simply now my secondary circuit of imaginary induction motor turns out to be there exists a E2 and also my R2 and some resistance and some reactance. So what is this value of this value? So if you see here, my imaginary induction motor is at standstill. So my E2 will be, sorry, my induced rotor voltage will be E2, and the leakage reactance is X2 because it's standstill condition, and my resistance is R2 by S. Please don't get confused. My slip of my imaginary induction motor is 1 only, but here the S is actual slip of the actual motor, the slip of my actual motor. That's where it comes into picture. Can anyone tell the frequency of the circuit? Rotor, how much is rotor frequency here? Again you are saying SF. There is no slip in the induction motor, right? Here in our imaginary induction motor, it's in standstill condition. Now whatever frequency is of my stator, the same frequency will be with my rotor because there is no slip here. So that's why I'm again telling you, don't get confused with this F's. I'm writing it separately here. So this R2 by S is a fixed number where we chose this R2 by S value for this standstill motor. Therefore my standstill condition is Fr is equals to Fs is equals to F. So my R2S value is a fixed number which I have calculated using the slip of my actual motor. And now if you calculate the I2 value here, I2 is equals to E2 divided by R2 by S whole square plus X2 square. Now let's say we have arrived at this current for my imaginary motor, and this is the current. This is current A of my actual motor, and this is current B of my imaginary motor. Are both A and B equal? Right? Exactly, A and B are exactly similar. The RMS value of my rotor current in both cases of A and B are exactly similar. Now, both currents are having same same current is flowing in the secondary of my rotor. So the field produced by my rotor is dependent on this current only. So because of flow, the flow of current will produce the field. Whenever the current flows through the turns, the field will be produced. So the rotor field produced in my rotor circuit will be same in both cases, A and B, and the strength of the fields, that is I'm talking about the magnetic field intensity, that is B, the strength of the magnetic field produced in the both circuits will also be same, because we are coming like a chain reaction. Because of the same current, same field will be produced. Because of the same field, the strength of the field will remain same, and because of my both equal strengths of my fields, my both fields will rotate with the same speed, that is synchronous speed. So the rotor field in case B, that is imaginary motor, and the rotor field rotor speed, I will just write it here, and in case A, this actual motor is very actually very interesting concept, and it's very simple and interesting concept. I2 responsible for RMF, rotor RMF is produced, and the same field strength and speed of rotor field is NS. And if you see the imaginary motor, same chain reaction will be there. Because of I2, same RMF is produced, same strength, the strength of the field will remain same, and also the speed of my rotor field will also be again as NS. In my both cases, a field of my rotor field is NS only. So now you tell me, let's go back to our stator, and I have placed a stationary observer on the stator of my actual motor, and I have placed a stationary observer on my imaginary motor. Now these two stationary observers are observing the actual running machine. One person is observing the actual running machine, and one another stationary observer is observing the imaginary standstill machine. Don't forget, my imaginary motor is at standstill condition. It's at standstill condition. Now whenever I am telling that sorry, whenever a stationary observer is trying to look at these two machines, one is running actual running machine and one is imaginary standstill, he would never be able to distinguish whether if it is a rotating machine or if it is standstill condition machines. Can anyone tell me why? Because for my condition A actual machines, it is rotating but having values of R2 and SX2, where X2 is a standstill reactance. My imaginary motor is at standstill but having R2 by S and X2. Now let's say I am the stationary observer. I am sitting on a actual rotating machine, stator of the actual rotating machine. I am observing the field of the rotor field. Now I have seen, okay, my rotor field is having a current of I2, and because of that I2 some field is being generated. I can see the rotating field of the rotor, and it is rotating with the synchronous speed of ns. Okay, I have decided that the speed of the rotor field is ns in first case, and I have come down of that stator, and I have sitting on the stator of my imaginary motor now. And again here I have seen the field created by the rotor current in this condition. Surprisingly, the field created by the rotor current in this condition is also same, because the RMS value of rotor currents in both conditions are exactly same. Here also my rotor field is again rotating with the same speed of ns, but surprisingly my imaginary motor is at standstill condition, but my actual motor is rotating with some slip. So the bottom point is, whatever might be the condition of my rotor, whatever might be it is open circuited or short circuited, if it is connected with some load, or it is open circuited, like it's rotating with some slip, if at all my rotor fields are rotating with the same speed, stator can never distinguish whether my secondary is rotating or secondary is at standstill. Now our main discussion came, why we started this whole discussion, because whether we can directly connect these primary and secondary circuits if we have a slip in picture. So that's what we started our discussion with, right? So now answering that point, how we proceeded with that question. To answer that question, we took an imaginary motor with the R2 by S resistance, that is a hand calculated resistance, and we made that imaginary motor as a standstill condition. Now in both condition we try to maintain the I2 remains same, and if you see, the magnitude of I2 is same and the power factor angle of I2. So if you see the power factor angle, that is nothing but tan inverse of imaginary component by real component. In the first case, if you see for the case A power factor, it is Sx2 by R2, and for case B, power factor angle is equals to tan inverse of x2 divided by R2 by S. In this both conditions you have the same power factor angle. You can see that. So now my stator will react in the same way in both cases, because both are drawing a current of I2. Now because in both these cases, I have told you, we just discussed in the transformer principle, whatever current drawn by the load I2, my stator will be forced to draw some external component, that is I2 dash, so that to compensate the MMF in the secondary. Now in these both conditions A and B, my stator side will always draw, same current in both A and B conditions. So that is very important here. So whatever might be the running condition of my motor, whether it is standstill or whether it is rotating motor, if at all I am able to produce the same current in my rotor circuit, if I can make a current I2 that is flowing in the rotor same in both cases, my stator has to draw some current, that is I2 dash. So that should compensate the MMF produced by the secondary. So that's the point. So people took this as a solution for the problem. So in order to combine these two circuits, primary and secondary, where slip comes into picture, what people do, so they overcome this problem of joining these two circuits of primary and secondary when slip into the picture by making this small change. I'm drawing the primary. That is this very actually very interesting concept that has been taken in the induction machines, and if you understood this, it will be very interesting to analyze, because This is the primary side and E1, and this is the primary side. There is no change. Now I am drawing the actual motor secondary as E2, and this is the reactance, and this is the resistance. This is R2 and X2, SX2 and I2. Now this is of the actual motor. Now what people did, they have changed the equivalent circuit of actual motor, and they have interchanged this parameters of this equivalent circuit and made it into E2, X2 and R2 by S. Here I2 will flow, and this is the condition. What they took here is pretending my motor is a stationary motor, imagining my motor is a stationary motor, and at standstill condition they have made these changes into my actual motor. Now if you see, the frequency of the quantities here is F, the frequency of the quantities here is SF. So by pretending my motor is in standstill condition, my parameters will be changed like this. And if you see these two circuits now, I can combine these two. Why? I can simply without even discussing this concept, we can just quickly move forward, like, okay, as E2 it is SX2 and R2, you divide each component by slip, and then we will get this, and then we will combine these two. But what is the reason behind doing that? To know it is very important and it's very interesting. That's why we discussed this. So whatever might be the parameters of my rotor circuit, if at all I can make the same amount of current flow in the rotor, my stator can't distinguish what kind of motor is this, as long as my rotor field is rotating at the same speed. In this both condition, my rotor speed is ns here, and here also my rotor speed is ns. So my stator cannot say whether it is an actual motor or whatever you are pretending it's a standstill motor. It just have to draw additional current of I2 dash. In both the cases it's exactly same. Okay, the problem is solved now. But there is small concept which you need to which you need to keep in mind here. So because now if both circuits look identical to the stator, now my stator can't differentiate whether it is actual motor or whatever your imagined motor is. By just looking at the circuit, we can say, okay, both circuits are identical in every respect. My rotor current is same, my power factor angle is same, the flux that is the flux generated in the both cases is exactly same. But there exists a very massive difference in both cases, that is active power within the rotor circuit. Now that is never same in this both circuit. If you see, it's just a small change I have made. We have divided R2 by we have made the R2 as R2 by S, even though my I2 rotor current, rotor power factor angle and also my flux is same. What about the active power in these both two cases? Now if you see, what is the active power in my actual case? So let's say in the first circuit A, in the actual rotor circuit, what is the active power? Active power only contributes to the resistance, that you know that, right? Now P actual motor case is equals to I2 is the square I square R, that is the active power contribution, I2 square into R2, that is my actual motor's active power. Now if I take the imaginary motor's active power, I2 is same, but R2 changes to R2 by S, and now we know S is always less than 1. Now because of this, the active power in my secondary side of my imaginary motor goes much bigger than the actual motor's active power drawn. How come this difference is coming? How can you justify this difference? Because my stator is not able to differentiate it. My stator just draws some current proportional to this rotor current, and it will see that, okay, I have drawn some amount of current that is enough because my rotor is drawing same amount of current I2 in both cases. It's not able to differentiate it. But if you look into the secondary circuit, because of the change you have done, the active powers in both cases are pretty different. My imaginary motor is drawing much more power than the actual. Now, how to justify this act? So there comes the picture of mechanical power here. Don't think that our case is failing. Don't think that because of this change, okay, we were able to combine these two circuits, but you have failed in balancing the active power. No, the active power is also balanced here, and it is actually balanced in even exact values also. So if you look into that, how can we justify this? Because we already considered that my imaginary motor is at standstill, right? My motor is not moving. And when you say your motor is not moving, there is no opposing forces, because my at the motor shaft end there is no any friction, and there is no load, and nothing is there. But when you say in our actual motor my machine is actually running, whenever your machine is running, there exists some kind of opposing torques there. So what are the opposing torques in running condition? Let's say your motor is running and driving some load, there exist I'm just writing here. In actual case, my machine is running, right? There exists some opposing torques, that is friction torque or low torque. Combined of these two will exist. Now, whatever you are seeing the actual losses in the that I square R2, that is only copper losses, and whatever other losses apart from this copper losses, that also should be supplied by your current, stator current, right? Locally you have this I2 square R2 losses, but on shaft you will have this total motor power which is dissipated, or you can say that motor power is utilized there as some kind of mechanical power, in terms of mechanical power. So these two powers are together combined and supplied by the stationary in this actual motor case. That's why, along with, let's say in actual case, my motor's stationary has to supply for the copper losses locally and also for the mechanical losses, because the motor is running there. We have just seen the copper losses. We say that this is very less and this is very high, because R2 by is much more value than I square R2. But in imaginary case, you actually get only copper losses and there is no mechanical losses. That's why you have seen a difference there. Now even we can, by this discussion, we can even justify our fact even more precisely, because in this imaginary your copper losses will be high, I agree, but in actual case copper loss is low, but the additional losses corresponding here, you are making the stator draw some current, and in actual case your mechanical loss will also comes into picture, and your stator will be drawn the current which is related to both copper losses and also the mechanical losses. That's how you are getting the total power balance in this case as well. So don't get confused that why my active power is more in case of imaginary, because we have just interchanged it, and we want a circuit which is exactly similar in both aspects. So yes, even active power is also compensating, because in imaginary there is no mechanical movement, so your total losses will be much more here compared to the actual, where the copper losses will be some extent and the other part will be mechanical losses. So that's what, even in this case, is active power balance is can be seen here, and hence my R2 by S, that is in case of this imaginary, this R2 by S will actually take care of both copper losses locally and also the actual machine and also the mechanical power in the actual machine. That's how we can satisfy our fact, which is in the both circuits are equal in every respect. So here by looking at, you can see it, this is the mechanical loss and this is the copper losses in my actual motor, and this is the total whatever losses in the imaginary circuit. That's what we get here. That is because of R2 by S component. So I'm just writing a small relation we have just developed from it. Now if I want to get P mechanical, and let's say in my imaginary motor case, let's say x kilowatts is drawn by the stator in imaginary case. Now even in my actual motor case, there exists the combination is x only. So what can I say? P imaginary motor case losses. Okay, if I subtract my P copper losses in actual motor, if I subtract this value from my total imaginary losses, what you will be left with? You will be left with this mechanical losses only, because that is what the additional component here. So yeah. So what I was saying is, your R2 by S component in your rotor circuit in imaginary motor, it is taking care of both copper losses in the actual motor as well as the mechanical losses in the actual motor. Now yeah, that is the R2 by S component, right? So if we take for total 3 phases, I'm writing it here. So what is the imaginary copper losses, motor losses in the imaginary motor? So yeah, this is I2 square R2 by S, I2 square R2 by S minus, what are the copper losses in actual motor? Those are the local copper losses, I2 square R2. So this one you will get as mechanical power that is developed in the motor, that is actually during the motor running condition. This is what it is needed for that. Now let's combine. I think we are running out of time. It's already 5:30 and in half an hour we have to solve the questions also. Let's I just want to explain it in a very detailed way of why this kind of concept came into picture of imaginary motor and fictitious motor, how we are combining these two equivalent circuits. That's why we are lagging a bit time. So let's complete our equivalent circuit now. Now equivalent circuit of 3-phase induction motor refer to stator side. Now with this kind of concept we can just easily remember our equivalent circuit as well. Now this is the primary and this is V1 and we have the magnetizing reactance here R1 and X1. Yeah, now we are combining the secondary of my imaginary motors to the primary, because E1 E2 is there, the ratio will be equal to the turns ratio, and we have a resistance component R2 by S here, and we can just multiply the turns ratio with the resistance component so that we can get a secondary side of this equivalent circuit. Now yeah, what is the reactance in the secondary side? It is A square X2 and the resistance will be A square R2 by S. And yeah, so this X2 is nothing but the standstill leakage reactance, and yeah, so yeah, we know that X1, X2, R1, R2 are very small quantities and there will be much less than magnetizing branch XM. So okay, so this is what the equivalent circuit of 3-phase induction motor would look like, and I can solve for the Thevenins and all. I hope the second session the TA will cover this, or else I can just quickly tell you, just look into this circuit because there exists a parallel branch. It's very difficult to solve problems if there is a parallel branch. What usually people will do, right? They will look from here and they will do the Thevenin's analysis, and they will come up with a circuit like this. If there is a VTH, and yeah, at this point, if you see these three branches will there, you find the RTH and XTH using the circuit analysis concepts, and you will have the same a square x2 and a square r2 by s here. So that way you will get the equivalent circuit without any parallel branch. So I will just write it here. Thevenin's voltage, that is V1, because if you see here, this is what the Thevenin's voltage is. I hope you also agree with that. So voltage across the magnetizing branch is nothing but the Thevenin's voltage. Now if you want to calculate it, it's V1 into JXM plus R1 plus JX1 plus XM, and it will be useful for solving the problems for this kind of concepts. And yeah, ZTH also, it's RTH plus JXTH. If you see what if you look at here, open voltage is if you see the equivalent impedance here, it is R1 and XM in parallel with the JXM. So what will be this one? R1 plus JX1 multiplied by JXM divided by R1 plus J into X1 plus XM. So this is the Thevenin's impedance and this is Thevenin's voltage. You do that, you replace the stator circuit like this so that you will get a Thevenin's equivalent circuit. So yeah, now you can also calculate the current in this case. Oh, shit. Actually, I wanted to discuss more on torque slip characteristics as well because that's important. So how we are getting different torques. Anyway, so yeah, in the Thevenin's case, you can just calculate the rotor side circuit, that is I2 dash, because I2 dash is the current referred to primary. Now it's nothing but VTH, that is the total input voltage, divided by the total RTH, Thevenin's resistance, rotor side resistance square, plus XTH plus X2 dash, that is referred to, it's R2 dash by S and it is X2 dash whole square. Now if you see, this is the rotor circuit, and here S is there. Now if you vary the slips from 0 to 1, you will get different kinds of rotor currents. Now yeah, that's what we want to discuss here. Now I don't think we have much time today, and let's go with solving the questions directly because I want to discuss more concepts such as what else, air gap power and the relation between air gap and okay, first solve the questions now, because that will be useful for you all to while solving the assignments. So if at all we have some time at the end, we will discuss some concepts on air gap power and power flow diagram in an induction motor. That is very easy concept. So yeah, let's start solving the questions. I want everyone to take the calculators with them, a piece of paper and pen, and let's start solving problems with me. And yeah, let's see the question. We are given a 3-phase 6-pole 50 Hz induction motor, and they say that the rotor is connected with a per phase standstill resistance of 0.25 and a reactance of 1 ohm, and when the stator is excited with the rated supply, the induced EMF in the rotor is 120 volts per phase at standstill condition. Now estimate the rotor current at the starting. So it's very simple question, and see, we know that they are not giving the equivalent circuit referred to stator or anything like that. They have just given star connected rotor is there, star connected stator is there, and they are just writing. So they have given the parameters of rotor circuit. Let's say there is rotor circuit here, and there is resistance and there is reactance here. And they said that standstill resistance is 0.25. So it's standstill condition. Can anyone tell what is the value of slip in standstill condition? And it is the value of slip in standstill condition is s equals to, it's not 0, it's 1. S equals to 0 means ns is equals to nr. Your rotor is rotating with the same speed as synchronous speed. Now here the rotor has no speed, it stands still, it's a locked condition. Nr equals to 0. If nr equals to 0, slip is 1. Okay. Now 120 volts also in standstill condition only. Now so what was asked here? Estimate the rotor current at starting. And one more thing, at starting condition means at starting nr is equal to 0. So there also you can say that slip is 1. So I2 at starting, I have written I2 because we are following this convention I2 as a rotor current. It is not referred to stator, that's why I have not kept the dash on as a superscript. So I2 is equals to E2, that is at standstill condition, divided by R2 at standstill square plus X2 at standstill square. Someone quickly calculate it and tell me what exactly answer is you are getting. R2 is 0.25 square and X2 is 1 square. I also calculate along with you, just we can just match the answers. So 116. So yeah, the rotor current in the standstill condition is 116.4171 amps. I hope you all got the same answer. So here it was given in the question that because it's a standstill. Standstill means the slip is 1, and substituting the formula of S equals to 1 in the circuit, you will get the E2 as 120. That is given because in the question it was mentioned that 120 is the voltage induced in the EMF at the standstill condition. So yeah, that's the rotor current in this at the starting position. Now if we let's go to the second question. We have to estimate the rotor power factor at the starting. So again, at the starting condition means the S is equals to 1, and for the power factor is nothing but the resistance component by the impedance component that we know. So cos phi will be rotor power factor. What is the resistance in the rotor power factor? That is R2. This and the total impedance, that is R2 square plus X2 square. There is no concept of slip again here because at the starting S equals to 1. Now what is the standstill resistance? 0.25 divided by 0.25 square plus X square. Can someone tell me the answer? 0.25 divided by 0.25 square plus 1 square. It's 0.2425. It's a power factor. You can see the starting power factor of an induction motor is very poor here. 0.24 power factor is very, very poor. And that's why people usually connect an external resistance in the rotor circuit at the starting. So that concept also I wanted to discuss today, but I think time is not sufficient. Later we will solve the problems on that as well. The technique is, initially if we could add some external resistance in the rotor, that will improve the power factor. We will see that later, but for that purpose we have to make an arrangement in the rotor circuit such that the terminals of the rotor are available at the end, so that we can connect some extra resistance at the starting, and then they can slowly remove that later. Anyhow, the power factor at the starting here is 0.2425. That's very less again. Now yeah, estimate the torque at the starting. Okay, we haven't even discussed the torque equation also, but anyway, we will just try to solve it for the in the torque equation directly. And yeah, we know torque is equals to air gap power by 2 pi ns. We can do this derivation if there is time, or even next week also if we are left with some time. I will discuss in detail how we have arrived at this formula. And also what exactly air gap power is all. If simply I want to say that let's say this is stator and this is rotor, and there is an air gap in between. Now stator we are giving the supply. Whatever power given to the stator, after supplying for the stator copper losses, whatever power is left, that is the air gap power, right? Once supplying the stator, it will enter the air gap, so that the power in this air gap is air gap power. So if you see the equivalent circuit here, I will just so here only I will write. Now I have some stator, and then I have the rotor here, and this is my stator supply, and this is the stator circuit, and here we have applied the Thevenin's there, right? That is RTH and XTH, and this is VTH. So here I have supplied some input power. Now after supplying for this core losses, whatever left is air gap power. This air gap power should supply to the copper losses here. There are also core losses. If we neglect the core losses, eddy current losses and all friction windage losses, so the air gap power should supply to this R2 by S. So that's why we write air gap power is 3I2 dash square into R2 by S. Someone has joined. Yeah. So yeah, this is the air gap power. I'm just simply giving you a brief picture of how the air gap power we are getting. So 3I2 square R2 by S. It's the air gap power which we got here. And at the starting means S is equals to 1. We know that. So PAG is equals to P copper losses. At the starting, if we keep S equals to 1, 3I2 square R2. So that is nothing but the local copper losses which we saw before in the actual motor. Now, yeah, what is the copper losses what is the rotor copper losses in this condition? That's the, if we calculate that and we divide it with the 2 pi ns, we will get the torque. Now let's calculate the P rotor copper losses in this condition. That is 3I2 square R2 and 3 into we already calculated the rotor current in the starting condition in the previous problem, that is 116.417 whole square. 116.417 whole square multiplied by R2. How much is this? 417 square multiplied by 0.25. So it's 10164.68 watts. It is 10.164 kilowatts. Yeah, now we got the rotor copper losses at the starting condition. Now we have seen that at starting rotor copper losses are nothing but the air gap power, and now we can calculate torque, that is air gap power divided by 2 pi ns. But before that, let's calculate what is ns. Ns is nothing but 2f by p, which is in RPS, mechanical RPS, and f is supply frequency. 2 into 50 by how many poles they have said in the question? It's a 6-pole machine, and 50 by 3 ns. Now torque is equals to 10164.688 divided by 2 into 50 by 3, it is ns into 2 pi. Now can someone calculate this? Answer divided by 4 pi into 50 into 3. Okay. 2f by p is 50 by 3. Sorry. That's 2 is cancelled. 50 by 3 into 2 pi. It's 48.2. It is 97.065 Newton meter. So yeah, this is the torque formula. Actually torque is but power divided by 2 pi ns, and here we are calculating air gap power at the starting is nothing but the rotor copper losses, because at the starting s equals to 1. And with that we have calculated air gap power, and ns is nothing but 2f by p. It's a 6-pole 50 Hz frequency machine, so we calculated the torque developed in it. And the next question is, find the rotor current at a speed of 960. So here they are saying that my rotor is not standstill anymore. It is rotating with the speed of 960 rpm. Now rpm means rotations per minute, and r is equals to r60 rpm. Now let's calculate ns. Ns is equals to 120 f by p. 120 into 50 by 6, it is 1000 rpm. Now whenever my rotor is rotating with some speed, there comes the concept of slip. Now ns minus nr by ns is equals to 1000 minus 960 by 1000. So how much is the slip of my machine? 1000 minus 960, 1000, it's 0.04. It is having a 4% slip now. Okay, we have calculated slip. What we need to calculate exactly? We have to calculate the rotor current. Now, yeah, if we have slip in picture, we know the formula is SE2 divided by R2 square plus SX2 square. What is the slip? 0.04. E2 is the standstill rotor induced EMF, that is 120. It is given in the question. Someone has joined. Yeah, and R2 is the again our resistance, 0.25 square plus S into X2, 4% slip multiplied by 1 square. Now yeah, please calculate this. 0.04 multiplied by 120 divided by 0.25 square plus 0.04 square. 18.95 amperes. It's the rotor current at a speed of 960. You have to understand this. At the starting current we have got in terms of in hundreds order, 116 or something. Here you can see the rotor current has come down to 18 amperes when it is running. So the starting current of motor will always be very much high compared to the running condition current. So you have to take care of the starting current as well. Now let's see what is the power factor of my rotor at a speed of 960. So power factor, we already saw it is resistance by impedance. So R2 square plus here slip comes into picture. Now R2 is 0.25 divided by 0.25 square plus 0.04 square multiplied by 1. X2 is 1. How much is this starting power power factor of my rotor here? 0.04 square. Now you see the running power factor of my motor is 0.97. Very good power factor my machine is having at the running condition. So that's the difference. Now at the starting condition you see there is no slip there, and also there is no extra resistance. R2 is there. Now my power factor because of that condition is very poor, 0.24 something we got at the starting. Now here whenever my rotor is rotating with some speed 960 rpm, we got a very good power factor here. Okay, now the torque at this speed of 960, again the torque the formula is equals to air gap power by 2 pi ns, and we know that P rotor copper losses is equals to 3I2 dash square R2, and air gap power is 3I2 square R2 by S. And let's calculate the air gap power here itself. 3 into what is the rotor current at R 960 rpm? We calculated that 18.95. 18.95 square into R2, that is 0.25 divided by slip. Sorry, it is 0.04. So how much is my air gap power? 18.95 square multiplied by 0.25 divided by slip 0.04. Now I have got a 6.73317 kilowatts of air gap power. Now let's calculate NS. NS is 2F by P, 2 into 50 by 6, it's 50 by 3. Now again 6.73317 divided by 2 pi into 50 by 3. Now someone calculate it. Sorry. Hundred by 673. It's 64.297 Newton meter. This is the torque of a motor at the speed of 960 rpm. Okay, now comes the interesting part. The final three questions are interesting. If you see the questions, so we are considering the same motor 1 to 6, but now we are connecting an external resistance of 1 ohms per phase to the rotor. Now at the rotor we are having a 0.25 ohms resistance that we all know. Now what they are saying is, let's say I have added some kind of external resistance to the rotor circuit, so that my effective resistance is now 0.25 plus 1 ohm. So it's now my rotor resistance is 1.25. Now my rotor resistance is 1.25. So yeah, now with this additional resistance, we will see what my rotor current will be at the starting again. Now see, R external we added is 1 ohm per phase. Now we have to calculate I2 at starting. Now I2 when R external is connected, we know at starting means S is equals to again 1. There is no doubt in that. Standstill means S equals to 1. Now formula is SE2. Now my resistance is R2 plus R external. This is the combined resistance, right? S2 square plus X2 SX2 whole square. Okay, anyway, S is 1. Now my E2 will be 120 divided by R2 is 0.25, and this is 1 whole square, plus S is 1 and X2 is 1 square. Now what is my rotor starting current now? 120 divided by 1.25 square plus 1. At starting my rotor current is, someone has joined. Now my external, because of connecting external resistance, my current came down to 74.963 amps from 116 without external resistance. So one more added advantage or disadvantage that we can comment later, but because of adding an external resistance, my starting current of motor came down to 74.963 amperes. Now let's see the power factor at the starting when we added the external resistance. Power factor is equals to resistance part, that is R2 plus R external divided by effective resistance R2 plus impedance, R external square plus X2 square. SX2 in fact, but S is 1 here at the starting. Now yeah, R2 is already 0.25. We have connected 1 ohms in the external circuit, and it is 1.25 square plus 1 square. Quickly calculate it, and 1.25 divided by 1.25 square plus 1. So yeah, now the starting power factor we got is somewhat better when compared to the starting power factor in previous case. It's 0.78 now. Previous it's how much? It is 0.242. Very poor power factor. It's a somewhat a better power factor now because of the additional resistance included in the rotor circuit. Now let's calculate the torque at the starting because of R external. Same, it is air gap power divided by 2 pi ns, and S is equals to 1. So air gap power is equals to rotor copper losses, which is nothing but 3 I2 dash square into R2. And now what is the rotor current in this condition? It is 74.963. It's the seventh question. 74.963 square into R2 is now R2 plus R external. That is a rotor circuit. So that is 0.25 plus 1. Now can someone tell me what is the answer here? 74.963 square multiplied by 1.25. It's 21 point. Okay, anyway, air gap power is 21072.942 watts. Now again, 21072.942 divided by 2 pi into 2f by p, that is 2 into f by p, that is 6 ball. Can someone calculate it for me? And this is 3 by 100 pi again. 2, 3. How much torque you are getting? I am getting 201.231 Newton meter. So yeah, so the change you have observed in this condition is whenever you have added external resistance, your starting torque has reduced, power factor has improved, and torque also. What is the torque we got at the starting? And we got 97 something. Here it is 200. Starting torque has improved. So whatever I'm saying is, I will discuss in detail in the next week. But I'm just saying, let's say this is your torque. Let's say this is slip from 0 to s equals to 0 to 1, and this is your torque, and this is the maximum torque at some slip, and this is the s equal to 1 means starting torque. So let's say this is the starting torque in this condition. Whenever you add some external resistance, your curve will be like this. Maximum torque won't change, but your starting torque will improve. So I will explain all this in the next week session. So why your maximum torque is not changing when we are adding resistance, and why your starting torque is improving. Everything I will just explain in the next session. So today we have no much time because we have discussed more in other concepts. So yeah, a quick summary of today's session. We have started with the equivalent circuit of three-phase induction motor, and how can we approach drawing an equivalent circuit of induction motor from the transformer's perspective, and then we have encountered a problem how to combine two circuits whenever the slip is in the picture, and then we discussed the concept of stator drawing an additional amount of current to counterbalance the MMF in the rotor circuit. There, by using that interesting concept, we have imagined a motor which is at that condition of standstill, and whatever our parameters are R2 by S, so that we can get that behavior, so that we can get a speed of both rotor fields as same synchronous speed, and we can combine it. So using that same RMF we have managed to develop in both actual motor and the fictitious motor, and by same current, same power factors, and same flux, we are able to generate a secondary circuit, and then we combined it with the first circuit. But we also said that saw how the active power is also getting balanced in this condition, because in the actual condition there will be a mechanical movement. So the current has to supply for that as well. So that is being taken care of this R2 by S component in the imaginary circuit. That's how we are getting power balance as well. And then we look at the final three-phase equivalent circuit, and we can combine that parallel branch with the series path using Thevenin circuit. And then we started solving the problems for today. 9 problems we have solved. Same concept, how to calculate the rotor circuit starting current, power factor, torque, and when we have done the same analysis in 3 conditions. First at the standstill, second at the running condition, and third at the condition where we have added the external resistance. So I hope today's session is useful for you all and understood the concepts which we have discussed, and we would have discussed more concepts if you have much more time, and I'm sure next week I'll be able to cover some concepts in this along with the next week's concept. So I hope you all have understood today's session. Yeah, Anil, I'm okay. Thank you. So yeah, Rajit, yeah, I didn't check the answer. Sorry, I was not looking at the screen here. Thank you. So yeah, if you have any questions, please raise the discussion in questions in the discussion forum. We will get back to you. And yeah, I hope you all understood today's session, and we will meet in the next week's session. Sorry for taking an extra 5 minutes of time. I know you will have another session from 7 p.m. So please attend that session as well. There, our next teacher will be discussing concepts on equivalent circuit and Thevenin's equivalent based circuit questions. Thank you, Ranjit. Thank you, and happy Holi to you all as well. Thank you, Nand Kumar. Thank you all. Happy Holi. See you next week. Yeah, thank you, Anil.